Okay, with dynamics and statics, they're all Newton's second law problems. Okay, so I'm going to show you how to use Newton's second law with dynamics and statics. Basically, we do the same thing every time. Okay, so Newton's second law. Newton's second law is, and this is how we're going to set it up, m times a is equal to each force added up. Now these are vectors, so these are vector sums, which means if you have one going in the opposite direction, then it becomes a negative. Basically, you take that direction into account. Oh, this is Fn. So however many forces there are, they'll always add up to ma. Okay, so the only difference between a statics and a dynamic situation is the value of a. This is the only thing that changes. Okay, so if we've got a static situation, statics, then a is equal to naught, right? A is also equal to naught if it's a constant velocity. So the maths here doesn't change. So if you've got constant velocity or zero velocity, which would be a static situation, then all the forces have to add up to zero. M times a is zero because a is zero. Okay. If you've got dynamics, I can spell maybe sometimes. Okay, then a is not zero. That's the only, a is not zero. Okay. Okay, so that's the only difference here. If you set up the problem exactly the same, whether we've got a dynamic system, which means it might be accelerating, or a static system, which means it's either in equilibrium or traveling at a constant velocity. Everything else is the same. The only thing that changes is the a. So how I teach you to do these is exactly the same for the dynamic situation. Okay, so let's rub that out. Okay, so for this problem, we've got a 20 kilogram thing hanging on the wall, and it's a static system, so that means our a is going to be zero. Okay, and we've got these two, we're trying to find the tension force here, and we've got these lengths of rope, right? We're trying to find the tension in both of these strings, and the distance between them is 15 centimeters, and the length of these strings are shown. Now, okay, I've drawn the same diagram over here, right, just to make it easier than having all these things drawn in. So what we're going to do is separate the forces into vertical components and horizontal components. So this T2, it pulls this way horizontally a little bit. Now this angle is going to be the same as this angle in here. So this alpha. Okay. So if that's the case, then this is like the hypotenuse, this angle here. So I've got T2, it's pulling this amount, T2 cos alpha. Okay. Then it's also pulling up. How much is it pulling up? So this is the opposite side to this hypotenuse. So we've got T2 sine of alpha. Okay. Do the same thing over here. This beta, this T1, is pulling to the right. T1, now this angle here is beta, same as this angle there. Okay, so T1 cos of beta. And it's pulling up T1, now this is opposite, this is hypotenuse, T1 sine of beta. Okay, so T1 is this, the hypotenuse side. Okay, this is the opposite side. Now we actually know what cos alpha, cos beta, because we know the lengths of, so that's to give us these angles here. So if we know the lengths here, we can work out what cos alpha, cos beta is. Now, the trick in this one is to see that this triangle here, the red one, must be a right angle here. Now that's not always going to be the case, but because of these lengths, we've got a 3, 4, 5 triangle. So this is 3 times 3, 3 times 4, 3 times 5. Okay, so 3, 4, 5 triangle gives us a 90 degree in there. So that makes the problem nice and easy because we can say, we already know, just change colors. Say if we want cos of alpha, okay, so cos of alpha, okay, so alpha's here, okay, so this is a right angle triangle, so our hypotenuse is 15, so I'm just looking at the red triangle, okay, so cos of alpha, so that's the adjacent and that side, so I've got 12 over 15, which is the same as divided both by 3 is 4 over 5, okay. Cos of beta, so cos of beta, that's 9 over 15. 9 over 15 is the same as 3 over 5. Okay, sine of alpha, not sine of alpha. We've got alpha, so we've got 9 over 15, which is 3 over 5, and sine of beta. So what have we got? Sine of beta, 12 over 15, right? Opposite over hypotenuse, which is 4 over 5. Okay, so we actually know all of these cos alpha, cos betas already. Okay, so the way we're going to do this, okay, I'm going to show you how to set these up for every problem. Okay, so we're going to have, firstly, remember it's Newton's second law, which we said was m times a equals F1 plus F2, all the forces, which are vectors, however many forces there are, add them all up, and we set them equal to m times a. So we're going to separate these up into vertical and horizontal. So this will give us either simultaneous equations to solve, or it'll solve one thing for us and then we can plug that bit in. So vertically, what have we got? Now remember, this is a 20 kilogram object, so there's a weight force. Weight force is 20 times g. Okay. So vertically, what do we have? We've got these ones pulling up, T2 sine of alpha, T1 sine of alpha, and this weight force pulling down. We can put it back on this diagram if we want, 20g. Okay, so we're going to write it out. M times A, I'm going to run out of space here, doesn't matter, equals T1, right? T1 sine of beta. So that's pulling up here. Pulling up here is plus T2 sine of alpha. Get rid of this line. Okay. And then, so you got these pulling up, this one pulling down, so minus 20g. So they're all the ones that are vertical direction, yeah? Up, up, down, okay? So horizontally, we've got m times a, so I'll write it out again, m times a. Horizontally, we've got this one pulling horizontal and this one pulling horizontal. So we've got T1 cos of beta. Now we're going to go minus, right? So the minus here, because this one is in the opposite direction, this one's down and these two are up. So now I've got this one pulling right and then this one pulling left. So T2 cos of alpha. Okay. Now let's tidy these up a little bit. So that's basically the hardest bit, and the rest is just easy because a is 0. So I've got m times 0 equals all this. So this is just going to be 0. So let me just write in 0. M times 0 equals all of this. I could rewrite it out again, but I know what these sine alphas and sine betas are. We worked them out. So sine alpha or sine beta is 4/5. So right, 4/5 T1 plus sine of alpha is 3/5. So 3/5 T2 minus 20g. Right. M times a. Now a is 0. We've got a static system. Means it's not moving, it's not accelerating. So cos of beta is 3/5. So 3/5 T1 minus cos of alpha, that's 4/5. 4/5 T2. Okay. So then I can just solve these two simultaneously. So I've got two unknowns, T1, T2, T1, T2. I can put it straight into the calculator if I've got one. If I don't, I can rearrange some of these things. Oh, that's supposed to be 3/5. I just can't write sometimes. T2. Okay, times both sides by 5. That will give me 100G for T1 plus 3T2. Okay, I can times both sides by 5 here, which gives me 0 equals 3T1 minus 4T2. So that gives me T1 is equal to 4/3 of T2. And I can put that in here if I wanted to. So all this is just simultaneous equation algebra. Yeah, all this is algebra. There's nothing tricky about it. So 4 times T1, 4/3 of T2 plus 3T2. So I substituted this in for T1 into there. So what does that give me? That gives me, times it all by 3. Let's go 300G. That's just to get rid of this denominator. 16T2 plus 9T2. So that's 25T2. 300G. So that gives me 300 divided by 25 is 12. So I get T2 equals 12G. Done. Okay, so there's my T2 and my T1. T1 substitute back in here. 4/3 of T2, which is times 12G, which is divided by 3 is 4, so that's 16G. Okay, and there we go. I can type those in if I need to into my calculator. And gives me 156.8 newtons. And this one is 117.6 newtons. Okay. All right. So that's basically how we do them all. Let's do another one while we're still going. Just check if we're recording still. Yep, still recording. Still seem to be recording. So let's get rid of this one. And do another one. Okay. So the next one we're going to do, we've got another static situation and our object is acted upon with 3 forces, 5 newtons, 6 newtons, 60 degrees between them. And we're trying to find what force, we know it's acted upon by another force somewhere this way, so that it's in static equilibrium. So what is this force? Now, if we're finding force, we also need to find the angle. Now we can define where that angle is if we like. Okay, so if we do it on the horizontal here. Okay, so how do we do this one? Exactly the same way. We're going to say, well, this force is pulling this way a little bit. So this is F cos of theta. And it's pulling down, F sine of theta. Okay, so that one's pulling this one. This one is also pulling up. So this is this 6 Newton one, it's pulling up. Okay, and it's also pulling across. Okay, so if we call, this is also going to be 60 degrees in there. So that's Z angle. So this one's going to be 6 cos of 60. Cos of 60 is 1/2, so this one's 3 newtons this way. And upwards, 6 sine of 60. which is root 3 on 2. Yeah, so 6 root 3 on 2 is 3 root 3. 3 root 3. Beautiful. Okay, so we've got 3 newtons pulling this way, 3 root 3 pulling up, and then we've got pulling this one, F cos theta, F sine theta that way, as well as this one pulling this way. Okay, so separate it up into 2 sections. We've got vertical and horizontal. So let's go vertical, horizontal. Okay, so horizontally, what do we have? We've got this way. Okay, so we'll go m times a equals 5 newtons this way, this one, 3 newtons this way, minus this one pulling this way, F cos of theta. Okay, what about vertically? We've got this one up, so we've got m times a equals this one up, 3 root 3, and then minus this one, minus F sine of theta. Okay, so let's stick in, well, we know A is 0, so a static situation. So A is 0, so m times A, that's going to be 0. Yeah, so I've got 0 equals 3 root 3 minus F sine of theta. And here we've got 0 equals F5 plus 3 is 8 minus F cos of theta. Okay, so now I've got F, rearrange, F sine of theta. This is all just algebra. F cos theta, a little bit of trigonometry, a little bit of algebra, and we've got it. Okay, so we can put that into our calculator, solve simultaneously, and we've got it. We could do it by hand if we needed to, and say, to a degree, we could do it by hand. So we go we know F sine squared theta plus cos squared theta has to equal 1. So if we square both of these sides, right, so if I can get, well, I know that sine squared theta would have to be root 3 on 3 on F squared. So what's this squared? This is 3 times 3 is 9, times 3 is 27, so 27 on F squared. And cos squared theta is 8 squared is 64 on F squared. Okay, so put it into this identity. I know that 27 on F squared plus 64 on F squared has to be equal to 1. Okay, so now I get 27 plus 64 has to equal F squared, just multiplying both sides by F squared. And 27 plus 64 is 91. And therefore F is equal to root 91. Okay, so if F is equal to root 91, I put it in here, and then find theta. So it says theta inverse cos 8 on root 91, and that's approximately 33 degrees. Okay. Okay, so this angle in here, 33 degrees. Okay, let me just check if we're still recording. We seem to be. Still recording, so let me just show you. So this is basically how we do every single one. Now, in the textbook, it's sometimes they use different notation, so they might use the I, J, and K notation, or the I and J notation for it's only going to be in 2 dimensions, so that makes it pretty easy. I don't want to put too much. Liquid on there. That's not going to dry. Okay. Oops, got a piece of paper. Dry that off. There we go. Oh, beautiful. All right, now you could do these ones there is a bit of a trick. Sometimes there's some shorter tricks to be able to do these ones, like Lami's theorem. If you've got three forces, like the one that we did before, so 5 newtons, let's do it again, 60, this was 6 newtons, and we were trying to find out this F, and we defined this bit as theta. So we could set this up using Lami's theorem and solve, because we have 3 forces, except the other way works for everything. This only works if we've got 3 forces, we're in static equilibrium. This is the only situation this is going to work for. Okay, so we can go F on sine of 60. Okay, now we got this force and its opposite angle has to equal, well, F on sine of its opposite angle has to equal this force, so 6 on its opposite angle here. So what's this angle? This is going to be 180 minus theta. 180 minus theta has to equal 5 sine of its opposite angle. So all of this one. So let's break this up. Let's go vertically. This is going to be 30 here. Here we've got 90. And here we've got theta. So this is 120 plus theta. Yeah. 120 plus theta. Okay. So we can set up our simultaneous equations from here. We can go, oops, drop the loop. There we go. All right, let's do it. Oh, hang on. Let's have a look at sine of 180 minus theta. Let's think of our unit circle for a minute. Unit circle, if we've got theta and 180 minus theta, these get to the same height or the same sine values. So this is 180 minus theta is the same. That's the same thing. So this is going to become just normal theta. Okay, 6 on sine theta. 120 plus theta. I don't know. I'm not really sure. So let's just leave it like that. That's fine. Okay, so here we've got one equation here. So we've got F is going to equal to, let's just use this bit, 6 sine of 60 over sine of theta. Sine of 60 is root 3 around 2, so you can put that in. That would make it 3 root 3 over sine theta equals F. So okay, that's equation 1, or F sine theta equals root 3 around 3. And then we could use this bit and this bit. Okay, so we can go F is equal to 5 sine of 60 over sine of 120 plus theta. Okay, and then we could solve those two equations simultaneously, use our CAS, find theta, find F, and we should get the same answer as we did before. We get F is equal to root 91, and theta is 33 degrees. Okay, so that's it.